So a rational function is a function that can be expressed as a ratio of two polynomial functions. So r of x is f of x over g of x, where f of x and g of x are polynomial functions, and g of x does not equal 0. So that's really important that we notice that we're introducing division into our problem or into our function. So g of x cannot be 0 because you cannot divide by 0. So since rational functions involve fractions, there may be values of x that are restricted from the domain. So if we let r of x be this function, x squared minus 9 over x minus 3, what values are restricted from the domain? When we look at the denominator, we notice that if you set x minus 3 equal to 0, you get x equals 3. So x equals 3 would be restricted from the domain. So what we're going to do is if x cannot equal 3, we're going to look at what happens as you get close to 3. So we want to focus on this table of values. So as you approach 3 from the left side, so 2.9, 2.99, and so on, and then as you approach 3 from the right side, 3.1, 3.01, and so on. So as you zoom in on x equals 3, where is your y value going? So that's what we're going to look at. So if you complete the table of values, you can pause the video if you need to, but I'm going to show the answers here. All you're doing is you're putting y equals x squared minus 9 divided by x minus 3 into your calculator. And what I highly suggest you pay attention to is that when you enter that in your calculator, make sure you put parentheses around the entire numerator and the entire denominator, or else you're going to miss every single one of these rational functions. So you want to keep the numerator together and the denominator together, so put parentheses around them. So when you do that, you should get the same values that I do. Okay, not too crazy, 5.9, 5.99, and so on. We notice that when x equals 3, that's undefined. Now some of the homework, depending on the book or the system you use, it'll say enter DNE, so it does not exist if it's undefined, and that's okay. All right, so then what we're going to look at is we want to describe the behavior of r of x as x approaches 3. So as x approaches 3, when you look at the table, it looks like from the left side of 3, it's getting closer to 6. And then from the right side of 3, as you come from the bottom in the table, it looks like it's also getting closer to 6 on the other side. Okay, so what we look at is we have this notation. As x approaches, so the arrow means approaches, 3 from the negative side, or from the left side, y approaches 6. As x approaches 3 from the right side, y approaches 6. So notice that when you look at the arrow, you're really using that term or word approaches. So as x approaches 3 from the left and right side, y approaches 6. And the way that we can write that is we use these concepts in calculus called limits. And we don't go too crazy with these in pre-calculus, but I just want to introduce you to the terminology and notation. So one way that we say that in calculus is the limit as x approaches 3 from the left of our function is, or equals, 6. And then the limit as x approaches 3 from the right side of our function r of x equals 6. Okay, so that is just the notation. That limit notation is just the way of saying this concept over here. That as x approaches 3 from the left or right side, what is the y value approaching? Okay, so if you sketch a graph of r of x, what happens is we have this line, and what happens is we have an open circle right here. So when x equals 3, you end up getting a hole in the graph. Okay, or what kind of discontinuity? So in part E, that's a removable discontinuity at x equals 3. I'm going to show you the graph in the calculator in just a second. But I want to look at part F first. So if you simplify that function and then evaluate the simplified version at x equals 3, well, when you simplify this, x squared minus 9 factors to x plus 3 times x minus 3. And that reduces. Notice how x minus 3 is a common factor. That reduces to x plus 3. And we know that y equals x plus 3 is just a linear function with a slope of 1 and a y-intercept of 3. But that only happens when x does not equal 3, because we can't just forget about dividing by the x minus 3. So this rational function is equivalent to this line at every point except when x equals 3, because x equals 3 is what is removed from the domain of this function, of the rational function. So I'm going to show you on the calculator what it looks like. So on the graphing calculator, I went and entered this function in. Notice I put parentheses around the numerator and parentheses around the denominator. So if I just do zoom 6 to graph it in the standard window, notice it looks like a line. But if I trace that line, if I put, say, 2.999 in, it gives me 5.999, and that was a value in the table. So now if I put 3 in, notice what happens. It gives me y equals, there's nothing there. Now it doesn't say undefined or DNE, it just doesn't show a value. So what's happening there, your calculator can't actually show the point plucked out of the graph. So this is where when you see this graph, you need to outsmart the calculator and understand what's going on. So we can see that when x equals 3, your function is undefined. So that's what happens when you graph in the calculator. And again, remember that you put parentheses around the entire numerator and denominator. So when you graph this yourself, make sure that you show the open circle on the graph. Okay, don't just sketch the straight line from the calculator. Make sure that you show the open circle. And generally what I like to do is put the x value there. And then in the case of a removable discontinuity, if you want, you can put the y value that goes with it. And the way you find that goes back to the last part of the question here, is that when you put your x equals 3 into your simplified version, x plus 3, so 3 plus 3 gives you 6. We could not put it in the rational function, but when we put it in the simplified version of that function, we get r of x equals 6, or your function equals 6. So what that tells you are the coordinates of the removable discontinuity is at the point 3, 6.